Okay, so I'm just talking about that. I hope you already practiced this type of velocity diagram. Okay, because I already told you have to draw it by yourself. Because these velocity diagram basically starting point while analysis of the turbine jet. That can be any turbine jet. So you have to draw the inlet and outlet velocity diagram, and then you can start analyzing different parameters. Okay, so this is the combined velocity diagram. This we already draw in the last lecture, and in most of the cases, the problems are not simple related to the impulse turbine or reaction turbine. That these type of combined velocity diagram you have to draw according to the scale, and then you can find out different parameters. That is the absolute velocity by measuring the length and then measuring the angles in between the lines for different beta one, beta two, alpha one, alpha two. Okay, so this sort of problems looks like this. But in this class, I'm not going towards more complex thing that I'm going to allow you to draw all these combined velocity diagram according to scale. So rather than I will provide all the data in the you can say figure. Okay, and you have to just put the formulas and directly calculate the values. Okay, so I have just make it simple. Okay, so coming towards the first question. Okay, so if you can read the statement, steam with absolute velocity 360 meter per second. So here it is mentioned at V1, that is the velocity that is coming at the outlet of your nozzle. Enters the stage of an impulse turbine. The nozzle are inclined at 20 degree. So it's mean alpha 1 is given in the question. To the plane of the wing, the blade rotor with diameter 95.5 centimeter rotates with a speed of 3000 rpm. So your main target is to find mean blade speed, power dweller, kinetic energy of steam leaving the stage. Okay, so if you can notice from the combined velocity diagram, so usually by using the data you have to draw these figures by yourself. But here I have already mentioned that this is the combined velocity diagram and all the parameters, that is V1 is mentioned, blade inlet angle is mentioned over there, blade outlet angle is mentioned over there, world velocity 1 plus world velocity 2 component. So this whole length is already given, that is 348 meter per second, and absolute velocity of steam at the exit. So V2 is also known to us. Okay, another point here is mentioned that find mean blade speed, and U is already known to us. So for example, if U is not mentioned in this diagram, so then how you can find the U? Okay, so you can have to draw this figure by yourself and now and also note down the data, and then you will see how to solve it. Okay, so now coming towards the solution. So the solution is very simple. So part A, you have to find mean blade speed. Okay, so you already know, we already noted mean blade speed with U. So U basically you can easily find pi diameter of the blade, number of RPM divided by 60. So this is the simple formula to calculate. If the diameter of the blade is given and number of RPM is given, so you can easily find out by putting the value in this formula. So 3.14, diameter of blade is mentioned 95.5 centimeter, so 0.955. Number of RPM 3000 and just divide by 60, so you will get the mean blade speed as 150 meter per second. So in case mean blade speed is not mentioned in the combined velocity diagram, so you can easily find out by using this data. So coming towards part B. So part B is to find power dwelling. So you already know the equation from which we can easily find mass flow rate VW1 plus VW2 U, which is the mean blade speed, divided by 1000. So we get into kilowatt. Okay, so here this important thing is that this is mass flow rate, and here you can assume that the mass flow rate is 1 kg per second. Okay, although sometimes it is mentioned in the problem statement that what type of mass flow value of mass flow rate you have to use, but here you can use 1 kg per second. So this value is 1. This whole VW1 plus VW2 is mentioned in the problem statement, that is 348. U we have find in the previous step 150 and by 1000, so you will get 52.2 kilowatt. So this is a simple thing from which you can find the power value. So coming towards part C. Part C is also very simple, that you have to find kinetic energy of steam leaving the stage. Okay, important thing is leaving the stage, that if for example, if here it is mentioned that you have to find kinetic energy at the inlet of the nozzle. Okay, so you have to use the absolute velocity at the inlet. Okay, here it is mentioned that this kinetic energy of steam leaving the state, so it means we have to use absolute velocity at outlet. Okay, so I can use half m. Okay, this is mass flow rate because all the term is in per kg, so that's why. And v 2 square. Okay, so this value is 1. V2 square is mentioned in the question, that is 126 whole square. So if you can convert, it will be equal to 79.38 Newton meter per kg. Okay, so this is the kinetic energy of C leaving the stage. Okay, so now the solution is complete. So the solution is very simple for this type of questions. So you can note it down, then we will go to next question.
सर ये आपने कन्वर्जन के बारे में क्या बताया?
कन्वर्जन के बारे में मैंने ये बताया आपको कि आप न्यूटन मीटर पर केजी में लेके आना, तो यू कैन यूज ओनली this one. So if you can put here kg per second and then meter square per second, so you can find out that this whole term is in, I think, in watt. Okay, so you can just figure it out at how to convert Newton meter per kg. Okay, so you have to make the unit consistent, that either you can use the watt. So if you want to calculate in power developed in kilowatt, so you can calculate the kinetic energy of steam also in watt. Okay, so it's up to you. Okay, so coming towards the next question. The next question is also very simple. Okay, so you have to read the statement first. The blade speed in impulse turbine is 300 meter per second. The same V1, U is given in the question, okay, which is the blade speed. Nozzle angle is 20. So alpha 1 is given. Total energy supplied to the blade 473 kilowatt. This I will tell you when we are going to solve the problem, where we have to use this total energy supplied to blade. Calculate for mass flow 1 kg per second. A part axial thrust per kg. Brake power, if mechanical efficiency is 90%, blade efficiency and stage efficiency. And the combined velocity diagram is shown over there. Beta 1 is equal to beta, which is 29.5, VW1 plus VW2 927.5, VA1 minus VA2 92.5, VR1 and VR2 is also given. So you have to note it down, all the data, and then we'll see how to solve it.
हर एग्जाम में डायग्राम गिवन होगी, खुद बनाएंगे उसको?
जी, एग्जाम में डायग्राम गिवन होगी. Okay, so coming towards the part A. So in part A, we already see the how to find axial thrust. So axial thrust, you need the axial velocity component. So mass flow rate into VA1 minus VA2. So if you can put the value 1 over there, and VA1 minus VA2, which is mentioned in the question, that 92.5, so it is equal to 92.5 Newton. Okay, so this is the part A solution. So part B, brake power. Okay, so brake power, basically brake power, whenever we denote that brake power, so it's mean that the power after there will be some friction losses. Okay, so if there is friction losses in your turbine blades, okay, so from that we can calculate the brake power if the mechanical efficiency is known to us, or otherwise we can find the mechanical efficiency as well. So here the simple formula that the power, okay, so power which is developed into mechanical efficiency, so eta mechanical. So this mechanical efficiency is mentioned in the question as well. So first we can find the power. So formula for power is the same, m Vw1 plus Vw2 into blade velocity divided by 1000. So if you can plug in all the value 1, 927 which is mentioned in the question, 300 is also mentioned in the question. So you will get the power which is 278.25 kilowatt. So now we have the power with us, so we can simply multiply with the efficiency which is mentioned in the part B, which is 90%, so 0.9, and it is equal to 250.425 kilowatt, so which is brake power. Okay, so this is how you can calculate brake power. So coming towards part number C. So in part C, we have to find the blade efficiency. So blade efficiency formula, we already see in the last class. So blade, you can say eta blade, which is equal to 2U VW1. Okay, so this is a simplified formula which we already see in the last lecture. VW2 divided by V1 square. So all the parameters are known to us. U is known to us. This parameter VW1 plus VW2 is known to us. V1 square is known to us. So simply you can plug all the values and you will get the blade efficiency, which is 3927.5 divided by 900 square, and it will equal to 0.688 and 68.8% of your blade efficiency. So this is the simple procedure for finding the blade efficiency. You can note it down, then move to the part D. Okay, so part D, which is the stage efficiency, so which is equal to work done per second, that work done on blade per second divided by energy supplied to the blade. Okay, so ES is basically energy supplied to the blade. Okay, so here the work done on blade per second we have already find in the P wave, which is the power value. Okay, so you can say that it will be equal to 278.25, okay, in the kilowatt. Okay, so energy supply is mentioned in the problem statement to the blade, which is 473. Okay, so if this data is not given, so then we have to give the helpless value and to find it. But in this case, the given it is given in the problem statement at 473, so we can use directly this figure, and it will be equal to 0.588, and it is equal to 58.8%. And I hope you already know that what is the meaning of stage. Stage is basically the combination of your stationary blade and a moving blade. So the stage efficiency is the efficiency of one set of the moving and your stationary blade. Okay, so this is the solution for this type of problem. So if you can see this sort of combined velocity diagram problem, so you can easily find out
सर ये
all the
पार्ट टू,
जी जी।
मेरे पार्ट बी दोबारा बता दें सर, ये समझ लगी।
अच्छा, पार्ट डी का फॉर्मूला हमने लास्ट क्लास में देखा था कि जो हम लोग स्टेज एफिशिएंसी निकालते हैं वो होती है वर्क डन ऑन ब्लेड पर सेकेंड divided by energy supplied to blade. Okay, so this is the formula for the stage efficiency. Okay, I hope you already know from the last class that this formula we have already discussed. Okay, so in this case, the work done on blade per second, m vw1 plus vw2 u. Okay, so this is in watt. Okay, so you need this value into kilowatt. Okay, because energy supplied to blade is available in the problem statement is also in kilowatt. Okay, so from this data, or either you can convert 473 into watt. Okay, so then you do not need this 1000 as well. Okay, so simply this value is mentioned in the question, and this value you can easily find out from all the available data, and this is 278.25, this whole term, which is the numerator, and denominator we have 473, and if we can find out, it will be equal to 0.588 and 58.8%. Okay,
यस
सर अगर एनर्जी सप्लाई ना दी होती तो फिर एंथैल्पीज कैसे फाइंड करते?
जी एंथैल्पी फाइंड करने का भी एक इसमें तरीका है, लेकिन उसके लिए आपको फिर टेबल्स भी चाहिए, और उसका एक अलग प्रोसीजर है. Although it is not a part of these lecture to find enthalpies in this rotodynamic machinery. So here you just notice that if energy supplied is given, so you can easily find out your stage efficiency. Because we are not going into much detail, otherwise this whole topic will be one course. Okay, that is the rotodynamic machine. Usually we offer in your elective courses as well. Okay, so till now you can just notice that if it is given, you can easily find out.
यस सर.
I hope you will get elective course in semester 7. Then you will get to know the detailed procedures, that how to draw all the velocity diagrams for all the types of blades, because there are many types of velocity diagrams. Okay, so this is just numerical section. Now we will just briefly look into some procedure. Okay, so also we are not going into much detail. The compounding of steam turbine is an important topic also. Okay, so what is the meaning of compounding? So this is another procedure which we most commonly use in most of the turbine, that how to reduce the wheel or rotor speed so that we can just obtain some optimal value. Okay, so compounding basically is the procedure, or sometimes we call it as a staging as well. Okay, so staging or compounding, the meaning are same. Okay, so if we can just take a look for the specific definition of compounding. So compounding is the way of reducing the wheel or rotor speed of the turbine to optimum value. It may be defined as a process of arranging the expansion of steam or the utilization of kinetic energy, or both in the several rates. So there are several methods of reducing the speed of rotor to lower value. And all these methods utilize a multiple system of rotor in series keyed on a common shaft, and the steam pressure or jet velocity is absorbed in stages as the steam flow over the blades. Okay, so there are various methods. So the most common is the velocity compounding, or you can say velocity staging and pressure staging, and also there is third type, which is the combination of pressure and velocity staging, and all the methods have the same objective, to reduce the wheel speed to the optimum value. So first we will look into velocity compounding, that what is the meaning of velocity compounding. So this is just a theory. So there are a number of moving blades separated by a ring of fixed blades. All the moving blades are keyed on a common shaft. When the steam passes through the nozzles, where it is expanded to condenser pressure, its velocity becomes very high. This high velocity steam then passes through a series of moving and fixed blades, and when the steam passes over the moving blade, its velocity decreases, and the function of the fixed blade is to redirect the steam flow without altering its velocity to the following next row of moving blades, where a work is done on them and steam leaves the turbine with allowed velocity as shown in diagram. So this is just a theory. I will give you the demonstration by using the velocity diagram and pressure diagram. Okay, so this is the velocity compounding. Okay, so if you can notice over there in the velocity compounding, we have the fixed nozzle, then we have the moving blade, then we have the fixed blade, moving blade, fixed blade, and moving blade. And if you can notice, the blade shape is same for the fixed and the moving blade. Okay, and the purpose of this fixed blade is just to redirect the flow. Okay, so for example, the flow is coming in this direction, then it's hit, and then again it will go back, and then okay, so in this type the flow will be continued. Okay, so the purpose of this fixed blade is just to redirect the flow in the right direction. So if we can take a look for the pressure and velocity graph. Okay, so the pressure at the end of the nozzle decreases, and then as it's moving towards the moving blade on the steam, it is constant. Again, fixed blade constant. Okay, through all the blade section, it remains constant in the velocity compounding turbine. Okay, so in this, the basically velocity compounding is just arrangement. Okay, we call it as arrangement. So in this type of arrangement, we have moving blade and fixed blade. Okay, and all the blades are of same shape. Then the velocity, we can see the velocity graph. So velocity, we already know that at the end of the nozzle is increase, then it's decrease, because definitely if it's hit the blade, so it's absorbs some kinetic energy and the velocity drop. Okay, but here there is a fixed blade, and fixed blade purpose is just to redirect the flow. It will not reduce any velocity in the fixed blade section. Okay, so the velocity remain constant throughout the fixed blade section. Then again, moving blade section, it decreases. Again, in the fixed blade section, it remains same, and at the end we get the decrease in velocity. So this is our main objective, to decrease the velocity so that we get the optimal value. Okay, so this optimal value is decided by the design engineer, that for example, if there is some specific purpose and for which they require some specific speed that our turbine will be run. Okay, so for that purpose we have to calculate that velocity, and from that velocity we can arrange our uh, stationary blades and moving blade. In that pattern we get that type of velocity, or in the that range of velocity as well. Okay, so this is the velocity compounding turbine. So this is just theory, okay, that I already explained to you. Okay, so it is just written over there, so you have to go through it by yourself. Okay, so there is nothing any which is difficult, so you can easily understand it. So here there is another term which is the pressure compounding. Okay, so pressure compounding is also basically the arrangement of different set of blades or your nozzle. Okay, so and we call it as a pressure compounding or pressure station. So these are the ring of moving blades which are kept on a same shaft in series, separated by ring of fixed nozzle. Okay, so in this case we have multiple nozzles that are you can say attached with the moving blade section. Okay, so the steam at a boiler pressure enters the first set of nozzle and expanded partially. The kinetic energy of steam thus obtained is absorbed by moving the blade. The steam is then expanded partially in a second set of nozzle where its pressure again fall and the velocity increases. The kinetic energy so obtained is absorbed by second ring of moving blade. This process repeated again and again, and at last steam leaves the turbine at low velocity and pressure. During the entire process, the pressure decreases continuously, but the velocity fluctuates as shown in diagram. So we will see the diagram so that you will get some understanding how pressure compoundings look like. Okay, so in the pressure compounding, the arrangement of your blades and nozzle will look like this: that we have the fixed nozzle, then moving blade, fixed nozzle, moving blade, fixed nozzle, moving blade, fixed nozzle, moving blade. Okay, so if the arrangement is like this, we call it as a pressure compounding. And sometimes we use a combination of pressure and velocity compounding so that we get the more optimal value of the velocity, or reduce the speed of the shaft, or you can say turbine, to the required value. Okay, so here in case of pressure compounding, the pressure decreases at the end of nozzle, then it's remain constant. Okay, because it is the moving blade section and the steam is directly hitting over there. Then we have steam, nozzle again. Okay, again it's decreasing. So in the case we get the reducing pressure at the end of the stage. Okay, so combined we count as a stage. Okay, so for example, this is stage 1, this is stage 2, and 3, 4. And if we want to require that our pressure will drop to certain value, so we can increase number of stages as per our requirement. So in the case of this, the velocity, we can see the velocity. So at the end of the nozzle, the velocity increases. Then in the moving section, definitely there is a absorb of kinetic energy. So your velocity decreases, again increases in the nozzle, then decreases, increases, decreases. So in the same pattern, we get the reduced velocity, or you can say for required value we get by using the pressure compounding. So these are just a procedure to reduce the turbine speed. Okay. So this is just for your information purpose. Okay, and this is a theory. So you have to go through it by yourself. It is a very simple and you can easily understand it. Okay, so another thing just for your information is that in the case of steam turbine, such as we are using for electric generation, a reaction turbine would require approximately double the number of blade rows as an impulse turbine for the same degree of thermal energy conversion. While this makes the reaction turbine much longer and heavier, the overall efficiency of reaction turbine is slightly higher than the equivalent impulse turbine. Okay, so from there you can easily find that reaction turbine efficiency is slightly higher than the impulse turbine for the same thermal energy conversion. But modern steam turbine that frequently employ both reaction and impulse in the same unit, typically varying the degree of reaction and impulse from the blade root to its periphery, and the rotor blades are usually designed like an impulse blade at the root and like a reaction blade at the tip. So if you can notice over there that this is an example of modern steam turbine blade. So where there is a at the root we have the impulse type structure of the blade, and at the tip we have the reaction type configuration. So what is the purpose of doing this? Okay, so the reason is that we have to develop such type of arrangement where we get the maximum efficiency. Okay, so for example, if you are doing some research and you can find out that in this arrangement we didn't get the maximum efficiency, rather than if we can take this middle portion out and replace it with some V-shaped blade, okay, so then it will give the maximum efficiency. So this is just a you can say arrangement by doing some research that you get the maximum efficiency, and then you can use this type of arrangement in the modern steam turbine. Okay, so there is no hard and fast rule why we are using impulse blade at the root or reaction blade at the tip. So you can use any type of configuration where we get the optimal value, or you can say the maximum efficiency of your turbine. Okay, so this is just end of this brief overview of the rotodynamic machines. Okay, and at this point we will just stop our thermodynamics 2 course. Okay, so if you have any question you can ask me, and then I will just give you some overview of the paper pattern as well after this. And next class, there is no next class, okay, on coming Monday or whenever in the next week. Okay, so this is just last class.
So फिर पैटर्न नहीं बता दें.
जी paper pattern. Okay, so coming towards paper pattern is basically whatever the course we have followed, that is the steam power plants. Okay, the Rankine cycle, reheat. So one question is from the steam power plants, one question is from the gas power plants, one question is from the uh, chemical reactions or gas mixtures. Okay, to combine, and then there is a compressor section, and this is the last. So there is total 5 questions, and we have covered the 5, you can say, specific domains as well. Okay, so there is nothing left. Okay, so you have to cover all the things.